When we talked about our electromagnetic wave entering an empty region of space, filling that space with both energy per volume, and we also said that it fills that electric and magnetic fields store momentum, so that there's a certain momentum per volume, that we found that the energy is related to the momentum, and you can see that if you just divide, if you multiply the momentum per volume by the factor c, you get the energy per volume. And so we can just say that the energy in this region of space is equal to the speed of light times the momentum that was stored in this region of space. Now, this relationship is very interesting because one can just say in another way that energy of an electromagnetic wave is related to the momentum that the electromagnetic carries by the factor c. Now, one of the key ideas in Einstein's theory of relativity is that there's a relationship between mass, energy, and momentum that's given by the famous formula that the rest mass of an object times the speed of light squared is equal to the, and we'll square this, is equal to the energy squared minus the factor c times the momentum squared. Now, Einstein conjectured this relationship, and it's how we define the rest mass of an object in terms of its energy and momentum. And that's a fun topic for you to explore on your own, or to look at some more courses on special relativity. But what I'd like to say here is that when we compare these results, one of the ways that we describe electromagnetic waves is in terms of it's a photon, which is massless. When we say massless photon, what we mean is that the rest mass of the photon is 0. But the photon can have energy, and from Einstein's relationship, we quickly get that E equals Cp, which is just is consistent with this classical picture of energy and momentum stored in an electromagnetic wave. When we considered a plane electromagnetic wave, we talked about an electric field that was a sinusoidal function, and it varied by kx minus omega t. Say this was one particular type of solution of a plane electromagnetic wave traveling in the positive x direction, pointing in the j direction, with an associated magnetic field that went down by a factor of 1 over c, and the magnetic field was pointing in the k-hat direction. And we talked about the energy density stored in this field, and we time averaged everything by looking at the energy density stored in the electric and the magnetic fields. Now, this is a wave that was oscillating, so what we had was that the angular frequency was 2 pi over the period, and our wave number k was 2 pi over lambda, and we saw that omega over k was equal to c, and so the angular frequency was c times k, which was c 2 pi over lambda. Now, Planck made a hypothesis that an electromagnetic wave can be described in terms of photons. And his hypothesis was this is a quantum of the electromagnetic field where the energy is related to the angular frequency by a constant h bar times omega. And h bar was equal to the Planck constant divided by 2 pi, where h is the Planck constant. Now, we saw that our electromagnetic wave was related to the momentum of the wave by the speed of light times the momentum. And if we combine these results, we have that h over 2 pi times the angular frequency is equal to c times the momentum. And let's now replace our result for the angular frequency, which is the speed of light times 2 pi over lambda equals Cp. And so another way of describing our quantum of electromagnetic energy, the photon, is that the momentum and the wavelength of our photon are related by this fundamental relationship: momentum times wavelength is Planck's constant.